All right. Hello, everybody. Hopefully you can hear me. Let me check my mic settings just in case. Good. Um, well, here it's Friday. I hope you guys are having a good start to your weekend. Hopefully we're sticking with our async work and getting that accomplished. Today, I'm going to be doing a lecture on earthquakes. It's going to be the very start of earthquakes. Earthquakes is definitely, I would consider, probably the hardest thing I teach in earth science. And it's not because necessarily the concepts themselves are difficult, but because they're really intangible, and also we don't have a whole lot of prior knowledge about this information up to this point. So bear with me. Pause when you need to pause. Take a break when you need to take a break. I am going to split this into two different lectures, so you'll have this over 2 weeks. And then be prepared with some questions when you come to class. Again, this material is difficult. I'd love to see you guys pop into class next week and have some questions ready to roll. Okay. Um, Still working on 2-1, but we're adding in 2 dash or 3-1 here for. Sorry, something's beeping. So we're adding in 3-1 here as well. 2-1, talking about the internal processes. We discussed that a lot last week, right? Layers of the earth, convection in the mantle, and what that does to Earth's crust, okay? Um, Bringing in 3-1, we haven't talked about not unit 3, standard 3 much yet. That's really the impact on humans, the hazards that occur because these crustal and oceanic plates are moving. Okay, so that's what we're kind of dipping our toe into this lesson, but a lot next lesson. All right, what do we already know? We already know the Earth has layers: crust, mantle, core. Those layers are made up of various materials. We know that because of density, that heavier materials sink. So as we get deeper in the layers, density increases. We know that the exterior layers then are going to be very light, made up of those light silicates and things like that. And then as we get further down in the layers, of course, we have more of those metals, which is why we think that the inner core is solid iron. Some say solid iron and nickel. That's debatable. And then we know that the outer core is pure liquid. And what I want you to think about, I'd love for you to pause the video after I pose this question. How do we know that? How do we know that? How do we have any kind of concept? I know we talked a little bit about it in class, in live class. How do we have any kind of concept of what might be down there if we can't even get through the crust? So we know from Wegener, right? We have to have a good amount of information for the scientific community to accept a theory like that. So what kind of information do you think that we have? And I want you to keep pondering that question. We're going to come back to it consistently over the next week and a half. We know the Earth's crust is broken, Earth's crust and upper mantle with the sphere, right, is broken into pieces called tectonic plates. We know at this point that those plates move based on convection in the mantle. They divide, divergent, they collide, convergent, they slide, transform. And those movements cause changes on Earth's surface, and those changes can affect us in catastrophic ways. So now what's next is we're going to look at earthquakes, all right? What happens when those plates get caught on each other, particularly at convergent and transform plate boundaries, right? Our divergent boundaries are usually very calm, and we looked at that in class. We pulled up the USGS website and we compared the number of earthquakes that were on a divergent plate boundary versus convergent and transform. So the movement of the plates can build tension, and that tension, if it catches on that rock, the convection continues underneath. It is building that tension, and what happens? What happens? Eventually, that tension must be released. And I think this is a collab board, so I'm going to move past that. We'll do that in live class, okay? Also, a couple of videos I'm going to skip through. I am going to do one video clip with the lecture. It will be in the notes, but I just think it's so pertinent to what we're learning today. I don't think I've done that yet, or maybe I have, but just once, and it's only about 3 minutes. So what is an earthquake? At certain boundaries, particularly, it can happen at divergent, right? But at particularly convergent and transform plate boundaries, and these are our volatile plate boundaries, right? There's a lot of pressure, there's a lot of tension building up here. The tension has to be released at some point, right? It can build up for years, it can build up for hundreds of years, it can build up for thousands of years, but eventually that tension is going to be released. and it's released in the form of seismic waves throughout Earth's layers, okay? And it can be devastating for us here on the surface if we are unprepared, especially if we're unprepared. The anatomy of the earthquake, this vocabulary is really what we're hitting home today. And you will see some different verbiage here. But the verbiage I went with for your notes is the verbiage that you will see in your progress learning tests, okay? So the anatomy of the earthquake, the very first thing is that we must identify the fault. The fault is the break in the crust, okay? And you can see that here, this line. And there are, when I was teaching face-to-face, boy, I got seriously into this stuff. But there are various types of faults, tension faults, normal faults. And depending on how that break is, it may slide out and down, or the land could slide in and up. But thankfully, after our standards changed, we don't have to teach those specific faults anymore. So you're not going to see that or be responsible for that. But you are responsible for the anatomy of the earthquake, the body of the earthquake. What does it look like? We have two major parts here. So we have the fault right here. That is the line in which the break occurs. Whoa, I did not mean to do that. All right, so that line right here is the fault line, okay? Next, we have the focus, and you might see this, and I get it, man, this makes so much more sense. You might see it called the hypofocus. Now, in making those tests in progress learning, I did not see that word. However, I mean, it makes so much more sense. I'm sorry, hypocenter. Makes so much more sense to have those two words that are similar, right? The focus is the exact point of that break, and you'll see that on the next slide. I have that for you to take notes. So if you're a note taker and you're writing this stuff down, it is on the next slide, but I want to talk through it on this picture. The focus is the exact point in which it breaks. All right, so that exact point where the rock is stuck and it breaks apart, that is the focus. These waves, these seismic waves, energy waves, go out in all directions from that point. Okay, so note that it's not just one direction, it goes out in all directions from that point, a circular pattern. The place above that, all right, so above, directly above, let me change colors here. It's already on there. Directly above where that break occurs is called the epicenter. Think to yourself, why would we need to have an epicenter? Why wouldn't we just, discuss the focus? Why do we need a word like that? Epi, if you've ever used an EpiPen or know somebody that does, or if you know much about biology, epidermis, epicardium, those words, that prefix itself means outside. Okay, so yeah, no, I don't know why scientists didn't just say epifocus, right, or something simple like that, so we could that vocabulary could be easier. But epicenter means outside of the center, outside of the center. Let's go on to the next one. Again, this is the notes slide, so I want you to pay close attention to this slide. This would be one that I would screenshot and put in my Unit 3 folder for review. The fault is the actual break, the break of the land, the scar, right? It's the break, it's the part of that land where the actual break occurs, okay? The epicenter, epi means outside. Center, of course, would be the focus or where it actually occurs. And then the focus again is the exact location of the break. But why would we need that term, epicenter? Why would that matter? I think it's a collab board too. I don't know why it's taking so long. Yeah. Why do you think seismologists need two different words for the location of an earthquake? And I don't think I have it on the next slide. Let's go back to this one so I have a picture. Why would we need that word? Well, because normal people wouldn't say something like, "Ladies and gentlemen, there has been a 5.2 magnitude earthquake that hit 22 degrees latitude, 722 degrees longitude." I have no idea if that's correct, or if that is not even a place. Just bear with me. And 21 miles deep. Nobody knows that. Nobody knows that. Nobody's going to know where that is. However, if you say, "Ladies and gentlemen, a 5.2 magnitude earthquake just hit Spartanburg, South Carolina," people are going to know where that is. So for scientists, knowing where that focus is extremely important, the exact location of that break, all right? But for layman's people like us, people that just want to know, hey, am I going to be affected? Or Or like, is anybody in my family affected? Did somebody I know get hit by this earthquake? The things that we really care about, right, are the places on the map. And that's why we have two different words, right? The epicenter is the place on the map where our news people can say, oh no, this is terrible. These people just experienced a catastrophic event. All right. Because again, the focus describing where that would be, no one would know. And so that is the reason that we have that extra word there. Here are some fault lines. We've already looked at this quite a bit in USGS. If you're in my class and you did live class with me, we've already looked at these. I am going to flip over to the USGS website here in a second, but these are fault lines. Now, I said in live class with you guys, I said, don't automatically hitch the word fault to a boundary because it's just not true. Okay. A fault can exist at a boundary and does exist at a boundary most often. So we talked about that boundary over here, the Pacific plate going up and to the left, the North American plate coming down and to the right. And so we talked about how this boundary over here, I hate that it goes brown every single time. This boundary over here, these two plates, is causing major destruction, right? San Andreas Fault, that's the transform plate boundary that goes through here, okay? Um, we talked about how it's just wreaking havoc on the land out there, right? So there are lots of fault chains. There's lots of breaks. And if you can think about it like maybe like a fracture in a bone, if you fracture your bone, there could be micro fractures that happen beyond that initial fracture. And that's what we're talking about here with the crust. Okay. So at this boundary, there is a fracture and there could be lots of little fractures, micro fractures that exist beyond because there's so much pressure on the land at this point. And those are all considered faults, and that's all well and good, right? But take a look over here. Look at these fault chains. All right, we saw lots in Texas. Look in South Carolina right there. If you've ever done a little bit of research on the Charleston earthquake and how bad that was, how many people that killed. So we do have a fault line here in South Carolina. We also have a major fault line in Tennessee that could do some damage as far as our upstate here in South Carolina. So it can be at a boundary. It is usually at a boundary, but it does not have to be. Okay, so I need y'all to understand that distinction. It doesn't have to be at a boundary. And so let's take a look, a gander over here at the USGS website. All right, this is the last 30 days. We'll just use the United States as an example. So look, are they close to boundaries? Do the majority of the earthquakes occur near a boundary? Yes, look at those. I don't even know the exact number there, but there's 9,636 earthquakes on here right now. Okay, and now it's all across the world, but um, yes, most of them occur near a plate boundary because of that microfracturing of the crust in those intense places. But again, check this out in South Carolina. Look, we have a fault chain here in Tennessee. Okay. And in South Carolina, look, we've had a couple small ones, right? But still, we have a fault line running through South Carolina as well. So again, I want to say it one more time. I know y'all love when I repeat myself. Faults can and usually occur near plate boundaries because of the intense pressure, but they do not have to. They can creep up anywhere under any part of any kind of continent that may have convection moving in different directions underneath. Okay, so it can occur anywhere. All right, here is the fault system in South Carolina. I won't give you a minute. I would encourage you to just kind of pause the lecture and take a look at that. Look at that. Is it surprising to you? Does it surprise you that there are this many in South Carolina? Is it surprising where they're located in South Carolina? And again, I'll ask you that in class, in live class. Are you surprised by what you see in South Carolina? Because it's not something that we've really experienced much, or most of us, right? This question is really important. Again, we'll do this in live class, but can we predict an earthquake? Can we predict? And we'll have some really good debate in class on that question. Be prepared for that one. The USGS website, I have a link here. I would encourage you to pause the video, go explore that, change in that website, change some of the settings. Oops, I think I was sharing the wrong tab. My bad. I'm gonna go back. Sorry. Go back. Okay. So this was South Carolina, the fault system within South Carolina. My bad, y'all. And then are you surprised by that? Can we predict an earthquake? And here's the USGS website. So my apologies for that. But I do want you to go play around with this website. I want you to like scroll out. I want you to change up maybe the magnitudes over here at the right. If you click settings, okay, you can choose, you can do the whole earthquake catalog if you want to. You can add population density, see how people might be affected. You could even put the U.S. faults on there. You could take the boundaries off. You could put the faults on there. We could change the magnitudes. Let's go for the minimal amount, and you can see just the fault lines here in the United States. Look at that. So again, that devastation on that plate boundary is what's causing it over there, okay? Let's see. You can add oceans. You can do all kinds of things here, guys. And then hazardous zones. Look, there's that Tennessee and South Carolina. Those hazardous zones right there. All right. So just play around with that website. It's pretty cool. Get some interesting information. And the more that you explore that website, the more you kind of you get the idea that that location matters for these earthquakes. Let me make sure it's not the video, I think. Oh, it is. I am going to play this for you on this because it is a brilliant explanation and visual of
Okay, so let's take a look at how to locate the epicenter of an earthquake using the triangulation method. All right, so here is a map of the world, and we're going to zoom in on a particular region. We'll look at North America, and let's imagine that there was an earthquake somewhere in North America. Well, the question arises, where was the epicenter of that earthquake? Now, we may be able to get a general idea of where the epicenter was based on looking at the severity of damage, eyewitness reports, etc. But if you want to pinpoint the actual location of the epicenter, you have to do some calculating. And so let's look at how we're going to do that. First off, in order to pinpoint the epicenter, you need a minimum of 3 seismic stations. So let's pop a few of these seismic stations on the map. Let's say we have one here in California, one up here in Canada, and one down south here, labeled 1, 2, and 3. Now, these are locations where we have seismometers actively monitoring the shaking in the Earth's crust. Of course, we have seismic stations all over the world. In order to use this triangulation method, we need at least 3 of these, or data from 3 of them. So, step 1 is going to be to take the data, the seismograms from each of these stations, and determine each of their epicenter distances. That is to say, I want to know how far point 1 is from the earthquake, how far point 2 is from the earthquake, and how far point 3 is from the earthquake. And this is fairly easily accomplished. You would simply find out the difference in arrival times for the P waves and S waves, and then use a travel time graph to calculate the distances. So let's say you have done that, and you have established that seismic station 1 is approximately 700 kilometers from the earthquake. So something like this. But the problem is, we don't know if it's 700 kilometers in this direction, in this direction, in this direction. We don't know. It could be 700 kilometers in any direction. So what we can do is draw a circle around point 1 with a radius of 700 kilometers. And now we know that the epicenter is somewhere on that circle, somewhere on that line. But again, that's not good enough because we want to pinpoint the location. So let's turn our attention to location 2 and say we did our math and we found that location 2 is 3,000 kilometers from the epicenter. Now again, it could be 3,000 kilometers in any direction. So we will draw a circle around point 2 with a radius of 3,000 kilometers. Now notice something. If you did this properly, your circles should intersect, most likely in 2 places. And what that means is that the earthquake had to happen either here at this intersection or here at this intersection. But again, that's not good enough because we want to know exactly where the epicenter was, which leads us to station 3. We take our seismogram, we do our math, and we determine that station 3 is approximately 3,500 kilometers from the epicenter. So Again, it could be in any direction. So we take a drawing compass and we draw our circle with radius 3,500 kilometers. Now, if this works out properly, all three circles should intersect in one single point. And that point is your epicenter, shown by the pink star. This is what we call the triangulation method for locating the earthquake epicenter.
All right, if that was overwhelming, don't worry. That was just your introduction. We're going to get into that, and we'll walk through that step by step with you, okay? Because that is a lot. That is pretty heavy. That's why I told you guys this is probably one of the hardest things I teach. So don't be overwhelmed by that. That was just dipping our toe in to what triangulation means. And we will be doing part of that in labs, but you'll be doing that, of course, after you have all of the information that you need. So don't be overwhelmed yet. Hopefully, you're kind of excited to do something like that and become a real seismologist. All right, so key vocabulary here that you need to take away from today. Under that seismic station there, you need to know what a seismograph is. And this one always gets kids because graph and gram sound familiar, right? Or similar. And graph kind of indicates that it's some kind of data. And so like these two words kids get mixed up a lot. Seismograph is the actual machine. It's the machine that's picking up on those seismic waves. It's the machine that is recording the data, okay? The data that comes out, the data that shows us when the P wave, S wave, and surface wave hit. And we'll get to those next lecture. But the data itself is called the seismogram. Now, it used to be that these printed out on a sheet, or it had this little scroll with this little pin that went back and forth as the earthquake occurred. Now it's way more technological than that. We have those seismographs that are deep within Earth's crust, and they are sending information back to large computers that are reading that information and sending it wherever else it needs to go. So a little bit more technologically savvy with those these days than what you might Google and find pictures of on the internet. Triangulation is what that guy just talked about in the video. Triangulation, tri meaning, I misspelled that, sorry guys. Triangulation, using data from 3 of these. Here's another error, my bad guys. These seismic stations, scientists can determine the epicenter of the earthquake, okay? We will study this more next lesson. We're going to talk about the different types of waves next lesson, P waves, S waves, surface waves, and then how to, in our lab, how to calculate the distance, the circumference that they were talking about in that video, and then using that information to locate the epicenter of the earthquake, okay? So no fear there. So I do on these notes have a couple of examples. I am going to kind of walk through this one with you. This is a little bit confusing, but in class we'll do a couple examples as well. So let's just say, I mean, these kind of look similar, but let's just say this one is number 1. All right, it's the shortest distance from the actual earthquake. Let's say this is number 2. All right, it's just a little bit further out here in Denver, Colorado. And this is number 3, and we know it's number 3 because it's the largest. It's a little bit further out from where the epicenter of the earthquake was. Where did it actually occur? And what we're looking for, what we're trying to identify here, which gets kids confused, but it's very simple, right? We are looking for where all 3 of these circles intersect. And you can see that they all touch, they all come together at one point right here in Albuquerque, New Mexico. And I'm going to leave this one for you, and then for you to try to do on your own. Again, you are looking for where all 3 of those circles intersect, not 2, all 3 of them. And then, of course, there is a time to climb, which we will do in class, but I do want you to do that on your own. All right, guys, that's all I have for you today. Looking forward to the next lesson with you and the live lessons where we're going to be doing a lot of this practice and hopefully getting some good questions from you guys. I hope you have a great weekend, and I will see you live next week.